Okay, welcome to discussion. Sorry about that. I guess it helps to hit to publish it, huh? There you go. All right. It looks like everybody hopefully got the announcement and all that. All right. Like I remember putting it in there. The little publishing is probably a good thing to have on, huh? Okay. So, like I said before, what we're going to do is we're going to continue lecturing, and part of this is chapter 5. So you'll be able to see it in your notes. It's the part about balancing equations and going about sort of balancing them. We're also then going to talk about, excuse me, we're going to talk about different ways to classify reactions, which is technically not in any chapter in our textbook, but it is part of the lab that I think you're doing this week. So we'll go over kind of the classifications. That you usually will cover in that lab. That way you should be in good and pretty good shape for the lab that's coming up on Wednesday for you guys. All right, so again, like I said, this first part here will be part of the notes that you should have from chapter 5 that we've been lecturing on. It actually should be pretty much right where we left off, I think. So we're going to talk about first, like I said, sort of balancing chemical equations, the steps to balance chemical equations. So when we look at an equation above, it is what is referred to as being a balanced chemical equation. And one of the things that we always want to make sure that we do when we deal with chemical equations is to make sure that it's balanced. And what that means is essentially, like the name implies, we pretty much have the exact same number of elements on both sides of the arrow. Um, so for example, on the left-hand side of the arrow, if we look at our hydrogen and oxygen, left-hand side, we have 4 hydrogens. Right-hand side, 2 times 2 is 4. Left-hand side, 2 oxygens. Right-hand side, 2 times 1 is 2 oxygens. So on the left-hand side and right-hand side of the arrow, we have exactly the same number of elements, and that makes it a balanced chemical equation. And pretty much in chemistry, anytime you're dealing with anything involving equations, you definitely want to make sure that you do make sure that it is balanced. Let's talk a little bit though about in a chemical equation, some of the different parts of it. On the left-hand side of the arrow, this side, those are the reactants, and the reactants are basically your starting materials in a chemical reaction. And they're always found on the left-hand side of the arrow. On the right-hand side of the arrow, they are the products, which are found on the right-hand side of the arrow. They are the things that are basically formed as a result of a chemical reaction. So your reactants are your starting materials. Your products are the guys that are formed as a result of it. So it's always reactants to products. Some other things that we commonly will sometimes see in an equation is actually on the arrow. We'll sometimes see things written there, sometimes a delta symbol. That usually means heat. You may see something like H plus, PT, something like that. Sometimes we will see what those guys are referred to as a catalyst. A catalyst is essentially not a reactant, not a product, but a lot of times a catalyst is added to a chemical equation or reaction, really chemical reaction to make it speed up. So sometimes in slow reactions, we add catalysts. They don't get used up. They don't, they're not considered reactants. They're not considered products. They're there usually just solely to make the reaction occur faster. So very common. You'll see that kind of put on top of the arrow. Sometimes you may even see like water put up on top of the arrow. And that usually implies that you took something and kind of dissolved it in water. So sometimes you'll see that used as well. In addition, in the actual chemical equation next to the formulas, we oftentimes will see like S, L, and G written, perhaps next to it. S meaning that the substance is in the solid state, L meaning it's in the liquid state, and G meaning it's in the gas state. Another common symbol that we see next to formulas is AQ. That means aqueous, and that's usually some type of water environment. And usually that is what's usually considered a solution. So sometimes people are curious sort of what the difference is between AQ and L. And the difference is L is a pure liquid. So for example, if I just took water by itself, that usually will get the L symbol next to it as it's a pure liquid, nothing in it, 100% water. Now, if I take water, which is a liquid, and I mix it with, say, sodium chloride, which is a solid. So if I take these two guys and put them together, sodium chloride will dissolve in the water, and it will give me a sodium chloride solution, which is aqueous. And again, aqueous usually implies that you took something, dissolved it in water, and made a solution. If something has just the L symbol, it implies that it's just a straight substance by itself, like pure water by itself, whatever else, anything that's just by itself, one thing. Aqueous usually means something has been taken and dissolved. So those are some very common sort of symbols that we see in equations. So let's talk about balancing equation. And the idea here is, as I mentioned earlier, you want to end up with the exact same number of elements on each side. So again, if you started with 4 carbons on the left-hand side of the arrow, you need to end with 4 carbons on the right-hand side of the arrow, maybe in different sort of molecules or substances on the right-hand side of the arrow, but you should end up with the exact same number. So first off, you want to make sure that you identify all the reactants and products, and you want to make sure that you actually start out with the correct formulas. So this would be a situation where maybe you're given everything in words, and you need to turn those words into correct formulas, and then you need to balance the equation. So it may not make a lot of sense right now what I'm going to say, but very often people sometimes try to balance the equation and write the chemical formula at the same time, and they end up getting the wrong formula, and they'll never able to balance the equation because they're not starting with the right formula. So this would be a situation perhaps where you're just given the left-hand side of the arrow and you need to predict what's on the right-hand side. And if you do that correctly, you want to first get the right formulas and then balance it. And very often people try to do both of those things at once. And like I said, usually does not end up very well. Usually they're a long time trying to balance it, and it just doesn't work really well. Next, what you want to do is you want to balance the equation. And when we balance an equation, the most important thing is the only thing that we change are the coefficients that come in front. So only the numbers in front. These are the only things that you can change when you go through and try to balance an equation. You cannot change the little numbers in a formula. You cannot, change the subscript like we have here. You can't put a big number in between or anything like that. So it is only the coefficients when you balance the equation. A, you can't change the little number because then you change what it is. And B, you can't put a big number in because you just don't do that. Most people, as we will see, do sort of a trial by error, kind of put a number here, put a number there. And eventually, if you sort of do it right, everything will sort of fall into place correctly. If you don't do it right, you'll be there a long time. But at some point, everything should fall into place. And what that means is you should make sure that when you're all done, you have the exact same number of elements on each side. And it's a good idea to check yourself, because I've seen a lot of people think, hey, it's balanced, and they don't have the same numbers on both sides. But most importantly as well is when you're done and you are balanced, there are 2 kind of rules that has to happen. First off, all of the coefficients, all of the numbers that come in front of the formulas, they need to be whole numbers. So they all need to be whole numbers, and they need to be the simplest set of whole numbers. And this could happen because some people could see larger numbers to balance it. Some people see maybe smaller numbers to balance an equation. So for example, if you did an equation where you had 2a plus 4b goes to 6c, and we'll just assume that it's all balanced here. Okay, maybe it's balanced, but if you look at all the coefficients here, you could technically reduce down all the coefficients by 2. So the properly balanced equation should be a plus 2b goes to 3c. And again, that happens sometimes as, you kind of put bigger numbers in and you could reduce them all down. So if you could reduce down all the coefficients by dividing by a common number, and it still gives you, again, all whole numbers, you should do that. If you can't do that, then you have probably the properly balanced equation, hopefully. That is usually sort of the path that most people take to balance these equations. So let's take a look at one together and kind of go through it. And I'll kind of show you how I would probably approach it. So you can maybe do the same thing. It would hopefully be helpful. So a lot of people sometimes don't do this and they just kind of jump in and start throwing numbers. I highly recommend you make a table. And sometimes when you make a table, you're essentially just putting down your elements. So nitrogen, oxygen, and hydrogen. We have the left-hand side, which is our reactant side. We have the right-hand side, which is our product side. And you just want to make a table of where you're starting with. So on the left-hand side, we have 1 nitrogen. Right-hand side, we have 2 nitrogens. Left-hand side, we have 1 oxygen. Right-hand side, we have 1 oxygen. Left-hand side, we have 2 hydrogens. And right-hand side, we have 2 hydrogens. So a lot of times this table will kind of give you a good idea where to start. If we look at our table here that we just made, we can see that we are balanced everywhere except for nitrogen. So that's probably a good place to start. So to fix the nitrogen, remember you could only do a coefficient. So we're going to put a 2 in front of the nitrogen on the left. When I do that, I now end up with 2 nitrogens. I have 2 oxygens, and I have now 2 hydrogens. And that is very common that once you fix one thing, something else gets screwed up. So here we fix the nitrogen, but now our oxygen is not correct. So what we want to do next is we can see from our table that probably going over to the oxygen side here would be a good place to start on that side. And to fix that, we would also put a 2 in front of the H2O. When I do that on the right-hand side, I end up with 2 nitrogens. 2 times 1 for the oxygen is 2. 2 times 2 for the hydrogen is 4. I have now balanced my nitrogen. I balanced my oxygen. The last thing I need to do to fix it would be come back here to the left-hand side, and I would need to put a 2 in front of the H2. And that gives me 2 nitrogens, 2 oxygens. 2 times 2 is 4 hydrogens. This would be balanced in this case. Again, only coefficients change, and that's a common sort of thing. Just kind of go back and forth. You could also see that you sometimes don't even have to touch a coefficient. You could just leave it as 1. Any questions on those steps? Okay. So why don't you try one here and see what you come up with. All right, so take a minute or two here and see what you come up with. So balance this equation. Okay, so let's take a look again, applying the same sort of approach here. We got carbon, hydrogen, and oxygen. Again, on the reactant side and product side, if we count up on the reactant side there, we got 3 carbons. On the product side, we have 1 carbon. Left-hand side, we have 8 hydrogens. Right-hand side, we have 2 hydrogens there. Left-hand side for oxygen, we have 2 oxygens. And on the right-hand side, we have 2 oxygens there and 1 more there, which makes 3 oxygens. So in this particular case, not much sort of balanced. So probably a good place to start would be the carbon. It's sort of probably the easiest. So we have 3 on one side and 1 on the other. So we could fix that by putting a 3 in front of our carbon on the right. When we do that, we end up with 3 carbons. Hydrogen is still 2. Oxygens, we are now up to 6 oxygens here, 3 times 2. We also have 1 more oxygen here. For that is 6, and 1 is 7 oxygens at this point. So we fixed the carbon. The next easiest thing to take care of would probably be the hydrogen. We have 8 on the left and 2 on the right. So we could put a 4 on the right-hand side. When we do that, we have 3 carbons. Hydrogen is 4 times 2, which is 8. Carbons, we have 6 still in the first guy, and now 4 times 1 is 4, and 6 is 10 oxygens. That means that the only thing left now is to balance our oxygens, so we can put a 5 on the left-hand side. That's going to give us 3 carbons, 8 hydrogens. 5 times 2 is 10 oxygens. Question on that particular one there. So again, you can kind of see as you go back and forth, eventually everything will really sort of fall into place. And again, you should have something that is balanced. Any questions on that one there? Okay. I got 10 for the, or talk about the oxygen. So on the right-hand side, let's see here. On the right-hand side for oxygen, we have 3 times 2, which is 6. And then we have 4 times 1, which is 4. So the 4 and the 6 gives us 10 for the oxygen. And then here we have 5 times 2, which would be 10 on the left-hand side. Other questions? So when you put a number in front, so for example, like we did there, when you put that number in front, it counts for both the carbon, which would be 3 times 1, which would be 3, and it would also count for the oxygen that goes behind it, which would be 3 times 2, which would be 6. So again, once you put that coefficient in front, it counts for everything that comes behind it, and you do need to account for the subscript as well. Other questions? Okay. Why don't you try this one then, see what you come up with. Balance out this reaction here. So that is a good question. The 3 actually only goes in this particular case to what's in the parentheses. So just the O and the H. Okay, so let's see how we're doing. So you can take the same approach. We got B, we got O, and H. So we have the reactant side, product side. On the reactant side there, we have two borons. On the product side, we have one. Oxygen on the left-hand side, there's three there, and one there gives us four. On the product side, as was asked, this three does go for both of the guys there in the parentheses only. So we would have three for the oxygen. And on the left-hand side for hydrogen, we have two. And again, multiplying that three in the parentheses gives us three. So not much going on in terms of balancing. We also don't have a tremendous choice here. So we might as well start with the boron and the right-hand side. So we will put a 2 in front of it. When we put the 2 in front of it, that does give us 2 for the boron. And now that we put that number in front, we do have a little bit of distributing to go. So we do need to take the 3 here, which would give me 3 oxygens, but we then also need to multiply it by the 2 on the outside. So again, the 2 goes for everybody that's there, but the 3 again only goes for the guys in the parentheses. So that would get us 6 in terms of the oxygen. Same idea, multiplying the 3 to the 1 hydrogen in the parentheses, and then 3 times the 2 on the outside gives me 6 for hydrogen. So you got to kind of distribute in and then distribute out in terms of the thing there to get the right number of guys, because essentially if you just kind of write it out longhand, again, we have 2 borons at this point. That is 3 and 6 and 3 and 6 of the hydrogens in that case. At this point, we balance the boron. Everything else is not balanced. We clearly don't want to mess with this number since it's kind of tied to everything. So we want to go to the other side and probably find the one that's the easiest to balance in this case. The easiest to balance in this case would probably be the hydrogen. And again, in this case on the left, we got oxygen and a couple of different things. So that's a little bit more complicated. So we could very much balance out the hydrogens by making a 3 in front of the H2O. What that does is gives me 2 borons. In terms of oxygen, on the first guy, I got 3. On the second guy, 3 times 1 is 3. So that is a grand total of 6. So by putting the 3 to fix the hydrogen, we actually just fix the oxygen as well, which oftentimes will happen. And then in terms of the hydrogen, we have 6. So this would be our correctly balanced equation. 1, we don't, again, don't put the 1 there. 3, 2 in terms of the coefficients. Again, we only change the coefficients in this case, nothing else. Any questions on that particular one there? All right, then give this one a go, see how you come up with. All right, see what you come up with on this particular one. Okay, let's take a look and see here. A couple answers, a few answers. Let's see how we did. So again, if we kind of look and see, we got nitrogen, hydrogen, and oxygen. We got R and P. So nitrogen, we have 1, and on the right-hand side, we have 1. Hydrogen, we have 3 on the left, and on the right, we have 2. Oxygen on the left, we have 2, and on the right, we have, again, 1 here and 1 there, which gives us 2. So everything looks pretty good. We got everything balanced except for hydrogen. So we want to start with hydrogen. In this case, we actually need to put a number on both sides. So we can put a 2 here to get a 6, which is our common number. And we could put a 3 on the right-hand side, again, to get our hydrogen to 6. When we put a 2 on the left-hand side, we end up with 2 nitrogens. We also end up with, in terms of hydrogen, 6. And in terms of oxygen, we end up with 2. On the right-hand side, we have 1 nitrogen still. Hydrogen is 3 times 2, which is 6. And oxygens, we have 1 still here and 3 on this side. It gives us 4 in that particular case. We fixed hydrogen, messed up everything else, which is very common. So what we want to do then is to fix probably what's next easiest, and that would be nitrogen. So we have 2 nitrogens on the left, we have 1 on the right. So we could easily fix that by putting a 2 in front of the nitrogen on the right. When we do that, that gives us 2 nitrogens. Hydrogen is still 3 times 2, which is 6. We then have 2 oxygens here and 3 more here. So that is 5. So at this point, we have now balanced everything except for oxygen. And when we look at what we have going on so far is we have, just to kind of clean it up. We don't want to obviously mess with any of these guys since we already put numbers. So that pretty much just leaves us one option as to where to go next, which is O2. We basically need to turn the 2 into the 5. And one way that you could do that is, as we see there in the chat box, is we could actually use a fraction to help us out. If we went 2NH3 plus 5 over 2, O2, gives us 2NO plus 3H2O. And that is because when we take 5 divided by 2 and multiply it by 2, the 2's cancel and we do end up with 5. So at this point, we do have 2 nitrogens on the left. We have 6 hydrogens on the left, and 5 halves times 2 gives us 5 oxygens on the left. Now, you may say to yourself, I thought everything had to be whole numbers when it's all said and done, and it does. But you can definitely use a fraction to balance something, and then you just need to clear the fraction. So to clear the fraction, what we need to do is multiply everybody by the denominator here. So we need to multiply the entire thing by 2 in this case, and that does give us 4NH3 plus 5O2 gives us 4NO plus 6H2O. And if we didn't screw anything up, we should still be 100% balanced still. We have 4 nitrogens on the left, 4 on the right. 4 times 3 is 12 hydrogens on the left. 6 times 2 is 12 hydrogens on the right. 5 times 2 is 10 oxygens on the left. We have 4 oxygens here, and 6 more here is 10. This is still balanced. So this is a very good example that you sometimes will need to perhaps use a fraction to balance it. It oftentimes happens, much like in this guy, where we have oxygen or some element by itself, and then in its elemental form, and then in a couple of things on the right-hand side, it's oftentimes is where you have to kind of use that fraction. You may also ask yourself, how do I know what fraction to use? It's a very simple sort of formula. So the top number, which was 5 in our case, in this example, was the number we need. So if you remember, we needed to turn that into a 5, so that's the number we needed. The bottom number should match this number down here. So that's a very good way, or easy way, to figure out what fraction you need. Top number should always be the number you're looking for or need. Bottom number should always match the subscript that you find on the element by itself. Again, usually happens when you get like N2O2H, something elemental diatomic by itself, and that same element in a couple of other ones. Question on that particular one there. Do you have to use a fraction 100% of the time? You don't always, but sometimes if you find yourself like, I can't figure out how to get it to sort of balance, you may want to look into a fraction, especially again if you have some diatomic element by itself on one side and that same element in a couple of things on the other side is usually where you come across it. Any questions on that? The properly balanced equation is the one in the box on the bottom, the one that has all whole numbers. So they got to all be whole numbers when you're all said and done. Why don't you try this one then and see what you come up with. Why don't we do FeSO4 plus Na3PO4 goes to Na2SO4 and Fe3PO4 2. All right, so see what you come up with on this one. Okay, so when you look at this guy, you could definitely approach it the same way as we approached everything else, kind of element by element. But if you also look at it, you'll see a couple of our favorite things, some polyatomic ions present. So we have SO4, which is sulfate on both sides. We also have phosphate on both sides. And sometimes when you're balancing equations, especially ones that have polyatomic ions on both sides, it is sometimes a lot easier to balance them by keeping those guys together and kind of balancing them as like units. Like I have one sulfate on this side, one on that side, one phosphate, two phosphates, rather than going element by element, because a lot of times you do element by element, there's a lot of like multiplying in and multiplying out because there's parentheses, there's polyatomic ions. So if I were to approach this one, what I would do is look at the sulfate. I got one SO4 on the left, I got one on the right, so that's all good. I would then look at the phosphate. I got one phosphate on the left and two of these guys on the right. So I could easily fix that by putting a 2 in front here. What that does is it gives me two phosphates, but then it also now gives me 2 times 3, which is 6 for our sodium. It also tells me where I should go next. It tells me perhaps I should go to the other side and fix my sodium now. And I could easily fix my sodium by putting a 3 in front. When I do that, that gives me my 6 sodiums, but now it also messes up my sulfate here and gives me 6 sulfates, which then tells me I probably should come back to this way and fix my sulfate by putting a 6 in front here. And when I do that, no, that's bad. I'm sorry. That gave me 6. I do math here. We're going to try math again here. So 3 times 1 sulfate gives me 3 sulfates. And that would fix it by putting a 3 in front of our iron. And that would give me 3 irons, which is what I need on this side. And also 3 sulfates, which is what I need on this side. So sometimes it's a lot easier to keep those polyatomic ions together as whole units and sort of balance them as units. And as you'll see here, usually what will happen is things will sort of fall into place like it did when I put the correct number here, which is 3, in terms of our iron. And rather than going element by element, you definitely could go element by element, but sometimes people make a lot of mistakes because there's a lot of multiplying in, multiplying out, parentheses and stuff like that. So if you do have these polyatomic ions that look exactly the same on both sides, I would keep them together and balance them correctly as sort of units rather than breaking them up element by element. Any questions on how to balance an equation? Again, only the coefficients, only thing that you should change, never anything else. And if you find yourself like it's really hard to balance it, it's not really working out, I would first check any formulas you've written because they're probably might be incorrect. And again, also look to maybe some type of fraction. But usually if you find yourself with an equation that's really hard to balance, it's usually that you don't have the right formulas down, especially if you have to sort of predict the formulas. Any questions on that there? So that is the official chapter 5 part of the lecture. We're now going to talk about the part of the lab and stuff that technically is not in any chapter anymore in this kind of new edition of the book that they got, but it is in your lab. So we're going to talk about how to classify reactions. And I'm just going to kind of hit the ones I think from my memory was in the lab or is in the lab. And just kind of do it by hand here. So we're going to talk about classifying reactions. And there are multiple ways you could classify the same reaction. We'll see a little bit of that as we go through it. But we're going to talk about sort of the classifications I think that are in that experiment. The first one I think that you have is a synthesis. And it's sometimes called a combination reaction. And much like the name implies, synthesis or combination, the way you recognize it is essentially you take 2 things and you make 1 thing. So kind of 2 things come together to make 1 thing. So for example, if I took some sodium metal plus some chlorine gas, I get some sodium chloride, put a 2 there. 2 things make 1 thing, classic combination or synthesis. The formation of water, H2 plus O2 makes some H2O. Again, 2 things make 1 thing. Classic way you can look at a reaction and identify it as a synthesis or combination reaction. And that's what you want to look at. You want to kind of think about the general sort of reaction that takes place and try to match it up to what you're looking at. Another classification, which is sort of the reverse of that, is what is known as a decomposition reaction. And that is essentially where you start with 1 thing and make 2 or more things. So kind of a synthesis or combination is putting it together. A decomposition is breaking it apart. So if we took an electrical current and run it through water, we would get a hydrogen gas and oxygen gas. One thing makes two things. Carbonic acid, which is H2O3, breaks apart really quickly into CO2 and water. One thing makes a couple of things. So your classic sort of decomposition reaction, again, starting with one thing, breaking it apart. So again, these two things are sort of opposites of each other. Combination, put it together. Decomposition, break it apart. Again, if you see just one thing on the reactant side and a couple things on the product side, probably going to be a decomposition reaction. Good way to recognize that. Any questions on that there? Another common classification is a single replacement reaction. And in a single replacement reaction, the way you can recognize is A plus BC. And if A is a metal, BC is an ionic compound, so a positive, negative guy together. And what's going to happen in this thing is this metal has no charge, so it's just the metal by itself. And the metal, when it does get a charge, is positive, and it will come in and kick out the positive guy there. And at that point, when it kicks out the positive guy, it will gain a positive charge, and it will hook up with the negative guy. And the B will come out with no charge over here. So that's your classic sort of single replacement reaction. One guy comes in, kicks out the other guy. In order for the guy coming in to do this, it needs to be more reactive than what it's replacing. So for example, if we take zinc metal, has no charge, and react it with hydrochloric acid, which is a positive negative guy. Zinc, when it does gain a charge, will be positive. It will come in and kick out the hydrogen. When it kicks out the hydrogen, what you get on the other side is the zinc will now get a charge and hook up with the chloride, and we will get hydrogen gas that will be formed. You'll see some bubbles and that type of stuff happen. And again, to balance this, we put a 2 here and so forth. Now, when I put the 2 here, I didn't put the 2 in front. If I had to predict what's happening on this side, what you want to think about is zinc, when it does get a charge, is +2. Chlorine, when it has a charge, is -1. So like we talked about with nomenclature, the correct formula when we put it together looks like this. So this is what I was talking about earlier, where you want to make sure that you get the right formula first and then you balance it. As you saw at the end, I went back and put a 2 to balance everything. I didn't worry about everything balancing at the beginning. You want to start out with the right formulas. And this is your classic single replacement. For example, if you did the same reaction, you started with copper metal. By the way, this has no charge on this side either. And you reacted with HCl, you would get no reaction. And that's because when it tries to come in, the copper is less reactive than the hydrogen in this particular case. So you would not get a reaction that would actually take place. So this is a classic sort of single replacement reaction involving a metal coming in and kicking out the positive guy. With the way the guy comes out, he has no charge. So if this happened to be a metal, the metal would come on this side with no charge. So if it was kicking out something like copper, copper would come up on this side with no charge. You could also do a single replacement reaction where the guy coming in is actually a non-metal. Plus BC, again, positive, negative. And in this case, the non-metal has no charge to begin with. But when a non-metal gets a charge, it is going to be negative. So in this case, it will come in and kick out the negative guy, and we will get a new ionic compound that will form. And that's when the A will actually get a negative charge. And what we will get is C will come out by itself. So this is very common, happens with the halogens. Same idea, the guy coming in needs to be more reactive than what it's replacing. So for example, here, if we took chlorine that has no charge to begin with and react it with sodium bromide, Again, this is a positive negative guy and a nonmetal by itself. The chlorine would come in and kick out the bromine. When it does, the chlorine then gets a charge of -1. The sodium has a +1 charge. So when those guys come together, the correct formula here is NaCl, not NaCl2. So you want to make sure that you get the right formula first. And then when the bromine comes out, it comes out as a diatomic molecule by itself. That's how bromine is when it's not attached to anything there. So has no charge. I have now all the correct formulas. Now I'm going to balance it by putting a 2 here and a 2 here. So this is the order like I've been telling you about. First, the right formulas, and then balance. I can't tell you how many people will lay up NaCl2 because they're like, oh, I got a 2 here. So that it must be the correct formula, and that is not the correct formula. So make sure you start with the correct formula first, and then you balance it. Same idea here. In order for something to take place, it does need to be more reactive. So for example, if you had I2 plus sodium chloride, it would try to come in and you would get no reaction. And what that would mean is I is less reactive than Cl, as opposed to here, if this reaction takes place, which it does, means that Cl is more reactive than Br. So if you see a reaction occur and it's sort of a single replacement reaction, that means whatever is coming in is definitely more reactive than what it's replacing. Questions on a single replacement reaction. So the way you can recognize it is one element by itself, no charge, not combined, plus something that's ionic, single replacement reaction. Now, the next type of classification is a double displacement reaction. And this is AB plus CD. How you recognize this is these both are ionic compounds. And in a double displacement reaction, what happens is the two positive guys switch partners. So the A ends up hooking up with the D to make a new ionic compound, and the C hooks up with the B to make a second new ionic compound. So for example, if we take NaCl plus silver nitrate, and that's all I'm given. And when I look at it, this is a positive negative guy. This is a positive negative guy, which means what I want to do is just think about the basic things that make these guys up. This is a sodium with a +1 charge, chloride with a -1 charge. This is silver with a +1 charge, and this is nitrate with a -1 charge. So when I want to write the formulas on the other side, just like we did with nomenclature, I just want to put these guys together correctly. The sodium and the nitrate will hook up. That's +1 and -1, which means I just need one of each. The silver and the chloride will also hook up. +1, -1. I need just one of each of those, and we will get our equation. At this point, I can go to balance it, which is balanced. Everything's the same on both sides. By the way, this double displacement reaction, this white solid that's formed, this silver chloride in this reaction, and because there's sometimes this white solid that's formed, it is sometimes what is known as a precipitate, PPT. And this is why this reaction is also sometimes classified as a precipitation reaction, because it made a solid. So it really is overall a double displacement reaction, but sometimes people will classify it as a precipitation reaction because it did make a solid. Question on that one there. Now, if we look at that last one that we balanced just a minute ago, in the balancing part, that also was a double displacement reaction. So if we look at what we started with on that one, which was FeSO4 plus Na3PO4, when I look at this, this is a positive negative guy, positive negative. Now, when we do this one, again, this is really important that you get the right formulas first. So basically what this is iron with a +2 charge. This is sulfate with a -2 charge. This guy is basically just a sodium ion, even though there's 3 of them. And this guy is really just the basic unit of phosphate. So what's going to happen is this positive guy will then hook up with the negative. This positive will hook up with the negative. And again, I want to make sure that I get the correct formulas. So when I put the iron with a +2 together with the phosphate with a -3, that's +2 and -3 is 6, which means the correct formula is Fe3PO4 2 plus the sodium, which is +1, and the sulfate, which is -2, means I need 2 sodiums and 1 sulfate. Now that I have all the correct formulas down, now I can balance it to take care of all my extra things, just like we did in the previous example, where I had the 3 here, the 2 here, and the 3 here. And now we can balance it to take care of everything that is unbalanced. But again, very often people will do something like this. Oh, this must be Na3SO4 because I have a 3 here and I need to get the 3 into my thing to keep it balanced. And again, if you try to do that, like balance and do the equation, you're going to get the wrong formula. So you want to first start with the right formulas and then go back and balance them. So that's really important to keep in mind. I think maybe in that lab, there's a few problems where you have to kind of predict what's on the other side of the arrow. So when you're predicting what's on the other side of the arrow, do it in that order. Correct equations and formulas first, correct formulas first, and then balance. Don't do them together. You will probably find yourself wrong formula and it will never balance. Question on double displacement reactions. The last type of classification I think you got going on in that lab is a combustion reaction. And really there's two definitions of a combustion reaction. There's sort of a general definition that basically says it involves O2 or oxygen. So if oxygen's involved, it's technically a combustion reaction. So if you have something like this, magnesium and oxygen makes some magnesium oxide. Technically, this is a combustion reaction because, again, there's oxygen involved. But if you look at this, you could also classify it, and it probably most often would be classified as two things make one thing, as a synthesis or combination reaction. So again, you could classify a reaction sometimes in multiple ways. Most people would probably go synthesis or combination, but it does meet the general definition of combustion. Although when most people think about a combustion reaction, they think about the organic combustion. And in organic combustion reaction, it usually involves something that contains carbon, hydrogen, and oxygen. So usually in an organic one, there's an organic compound plus O2 goes to CO2 plus water. That's your classic O2, always making CO2 and water on the product side when you're starting with something like carbon, hydrogen, and oxygen. That's there. So an example, like when you light a Bunsen burner, that is CH4 that comes out, plus some O2, always going to make CO2 plus water. Again, you could do some balancing, 1 carbon on each side, 4 hydrogens and 4 oxygens. But this is classic carbon and hydrogen here, O2 here, almost a safe bet to go CO2 and water on your product side. And that usually is what most people think about when they think about a combustion reaction. But again, in general, really a combustion reaction just has to have O2 in it. Anyway, questions on classifying different types of reactions. You kind of want to look at the general reaction for these guys and try to see is the one you're looking at sort of match up. Yeah, so the question is, let me see if I have something here. It's a good question. I'll give you the whole answer of everything going on that one. So what you have here is sodium carbonate plus some hydrochloric acid. And when you do that, what you actually make, this is truly, just so you could kind of see, this is truly a double displacement reaction. So the sodium here and the carbonate, and the H plus and the Cl minus. So the sodium and the chlorine will come together. Did I get the right one? I did right. So the sodium and the chloride will come together and make sodium chloride. The H plus and the CO3 will come together to make carbonic acid. So the overall reaction that's really taking place is a double displacement reaction where you can do some balancing, which I think we're put a 2 there and we're balanced. And this is really what's happening is a double displacement. But part of the double displacement reaction is it actually makes this guy, which I showed you earlier, which is carbonic acid. And that carbonic acid almost immediately goes through a decomposition reaction. And it decomposes into CO2 plus water. And that's why a lot of times people will kind of eliminate this part of it. And they'll get what you have up there, I think, with the sodium chloride and the, on this side, the sodium chloride plus the CO2 plus the water. And again, this part of it really comes from the decomposition of the first product that's made. So really what's happening in this case is you have a double displacement reaction followed by the decomposition of one of the products in this case. And one of those products is what you make the CO2, which is like the bubbling fizzing that you would see. In the case of yeah, so oxygen on the reaction side for the combustion reaction. And like I said, usually it's the organic one that you'll see. And in the case of the lighted splint, and just to kind of give you an idea what the what's going on there, is in order when you light a splint on fire, in order to keep a fire going, you need oxygen, right? So when you do this reaction, say in a beaker or a flask, a test tube, you're generating a lot of CO2. The CO2 replaces the oxygen. So when you put the fire lit splint in there, in the neck of it, it loses all the oxygen and you should see the fire go out. Basically, it'll extinguish it like a fire extinguisher, basically, because it's producing all that CO2 that's basically eliminating the oxygen. Yeah, so again, like I said, that oxygen on the combustion, on the reaction side, it is the generic sort of version of a combustion, and the organic would be, the organic one is usually what people think about. Other questions on that? So if I would have to classify it overall, I would say it's a double displacement reaction, but it is technically followed by a decomposition reaction of just that one product. I personally would probably classify the H2O2 making the water as a combination or synthesis reaction. But again, technically it meets that classification. You can classify a lot of reactions in multiple ways. If there was a choice of combination or synthesis, that probably would be the better classification for it than combustion. Because again, you could kind of almost apply combustion to a lot of different things. But sometimes you can classify the same reaction in multiple ways. Like the double displacement and the precipitation reactions, they're oftentimes classified. They're the same reaction, but you could classify it 2 different ways depending on sort of what you're looking at. Other questions? You're welcome. All right, well, I hope that helps. Again, like I said, the classification parts of these reactions you are responsible for, but it's not technically in your book, the actual textbook. It is in that lab, so hopefully this helped. And the balancing, obviously, is from chapter 5 as well. Other than that, thank you for hanging in there with me a little bit longer, and I apologize again about the link. I'll remember to hit the publish guy. I don't know how it got unclicked, but have a good rest of your night if you don't have any more questions, and I will see you on Wednesday. Make sure you put here if you haven't done so already.